Hello everyone, today I have the pleasure to present to you our work on private multi-winner voting for machine learning. My name is Adam Dziedzic and this is joint work with my collaborators. For standard computer vision datasets such as MNIST, we must find a single label per image. In this case, we label the digits in the image as 7. However, for many real-world datasets, especially in the medical domain, such as X-rays, we must label a given chest X-ray with possibly more than a single label, because a given patient might suffer from multiple pathologies. Now let us imagine that there is a new patient who comes to a hospital. The doctor has not had such a case before and is not confident about his or her diagnosis, so wishes to consult with other hospitals or doctors. The doctor takes a chest X-ray of the new patient and sends it to other hospitals. The hospitals then label the X-ray using their machine learning models and return the aggregated answer to the querying party. Intuitively, what we achieve is an analog of a doctor querying colleagues for a second opinion on difficult diagnosis. In our work, we formalize this workflow into a framework to achieve private consultation. However, there are two issues here. First, the answering hospitals do not want the liability for managing the private data about the new patient. And the patient would have to allow us to send his or her data to all these hospitals, which is a lot of paperwork. Thus, we need to ensure that the data of the new patient stays confidential. Second, because the doctors train their ML models on their patient-sensitive data, no information about this data should be leaked. This is why we want to privately release the output from the multi-label classification. We solved the first problem by applying the confidential and private collaborative learning framework called CaPC. This enables us to do private inference on encrypted data. Let us focus on how to prevent privacy leakage from the answering parties. Each of the answering parties, shown on the right-hand side, returns a binary vector with values for the three labels. Value 1 denotes a positive vote, and value 0 is a negative vote. There are two methods to aggregate the multi-label outputs. We can consider a single label at a time separately and assign positive or negative value to the label. The other method is Powerset, where we consider the whole binary vector as a single class. First, let's focus on binary multi-label classification. For a given label, we analyze the votes obtained from each answering party. In this case, we have positive votes from the first and the third answering party, whereas the second party returns the negative vote. Out of these votes, we generate a histogram and return argmax, in this case a positive vote, as an aggregation for this label. We provide the private binary multi-label classification via noisy argmax. We add Gaussian noise to vote counts in the histogram, where we leverage the PATE framework, and this is done according to differential privacy requirements. We apply this noisy argmax per label. This approach is intuitive. For the same amount of added noise, if the answering parties have high consensus, the privacy leakage is low, and the correct answer is returned. While for the low consensus, we have high privacy leakage, and the returned answer depends on the amount of added noise. In this case, we had 3 separate histograms per each of 3 labels. For each label, we create such histogram and take the noisy argmax to return the final set of labels. We cast multi-label classification as a multi-winner election and consider each label separately. Second, we also analyze alternative methods to the binary approach. So here, instead of considering per label classification, we take into account the power set of all possible votes, in this case, all possible binary vectors of size 3. Note that the number of classes grows exponentially in this method, which is to the power of n, where n is the number of labels. For the Powerset method, our histogram size increases to 8 classes instead of 2 per label. The whole binary vector from a given answering party is treated as a single class. Now let us consider a different example to compare our two methods, binary versus Powerset. In this case, each answering party returns different binary vector. but the majority votes per each label separately are positive. The binary method returns true plurality. Plurality means to select the most voted for label. The number of votes cast for a candidate is more than any other, but the candidate does not have to have absolute majority. Note that the selected labels are all ones, but such a binary vector was in neither of the returned binary vectors from the answering parties. A teacher does not have to perform well on all labels, but collectively the teachers returned correct answers. On the other hand, Powerset is an approximate method. The true plurality in this case is binary vector 1, 1, 1. The final returned answer here is 1, 0, 1, which is one of the binary votes. The Powerset method can return only one of the cast ballots cast of these votings. Thus, it only approximates the true plurality. Here we present data samples with uncorrelated labels, where a given label does not determine the other. The binary classification is optimal when we can release each label independently. We formally prove this optimality. And then, in the case of noisy or strongly correlated labels, the Powerset method performs better. For example, in this case, shown in this table, two last labels co-occur. So we add noise once to the entire binary vector instead of each time per label. However, many real-world datasets do not have many positive labels. A given patient might not have all the possible diseases that we can predict. For example, in the Pascal-Vogt dataset, there are on average fewer than 2 positive labels out of 20 in total. Thus, instead of allowing arbitrarily many votes, we restrict the votes in their L2 norm, which limits the sensitivity of the mechanism for the binary voting. The clipping is similar to the clipping in the DPHD algorithm. In this case, each answering party has the right to 2 positive votes. If they vote for more labels than 2, then we scale down their influence. For example, in this case, we limit the number of positive votes to 2. The squared norm of the binary vote is 2, and this is the finally clipped binary vector. For the Powerset voting, if we allow all 3 votes to be positive, then the number of positive classes is 8. Limiting the number of positive votes per a given answering party decreases the total number of possible classes. If we allow up to 1 positive vote per voting, then the number of possible classes decreases from 8 to 4. Before we can compare the multi-level classification using binary versus Powerset mechanisms, we define the metrics per label that are then averaged across all the labels. So here we use standard accuracy, but it is not always meaningful for the multi-level classification. So we also look at other metrics. For example, balance accuracy defined as an average of true positive rate and true negative rate. AUC is area under the curve, where the curve is rate between true positive rate and false positive rate. Finally, we also measure precision per label. Now we compare the performance of multiple classification mechanisms on the standard Pascal-Vogt dataset, which has 20 labels in total. We observe that across all the 4 metrics, binary method outperforms the Powerset method. Additionally, it also has much better performance than the standard DPHD algorithm. We also incorporate private multiple classification into the confidential and private collaborative learning framework called CaPC. We observe that models improve with the multi-label CaPC. In the first row in the table, we present performance of a model in a querying party before our method is applied. After the collaboration, where the querying party uses the new label data points to improve its local model, the performance of the model improves consistently across all the metrics. We also test multi-level CaPC on the standard mimic chest X-ray dataset. In this case, we also observe an improvement of models after the collaboration within our framework. This method can help hospitals to train better multi-level classification for chest X-ray while preserving security and privacy. Going back to the initial use case, our method enables the confidential multi-level classification via the CaPC framework. We achieve confidentiality with the CaPC framework by private inference on encrypted data. We also designed new binary and Powerset methods for private multi-level classification with the PATE framework. With that, I would like to thank you for your attention, and please post your questions to the comments or send me a message. Thank you very much.